then it will give us wildly different answers for the energy every time we measure that particle. So we'll have a wider distribution of energies, even though the original particle had the same amount of energy every time. So what we do is we run this experiment, and then we count over thousands or millions of these times of measuring this particle. And every time we measure an energy of a peak, we put it on a histogram. And a histogram is just a plot that measures how many times you count a specific amount of energy. So in these two histograms, we have energy on the x-axis and the number of times we measured that energy on the y-axis. So here, this would be an example of a detector with a good energy resolution. We see almost no energy counts for most energies except for the one specific energy of the particle that we were measuring. And at that point, it spikes. So almost every time the detector is measuring that specific energy. Whereas for a detector with a bad energy resolution, it seems as if this peak is spread out or blurred across the distribution of energy values. And this is the same process that we do all the time to characterize our detectors and or get to know them. So what does this tell us as researchers? If we have an experiment where we really want to know the energy and we make sure that it's reliable, then we need to pick a scintillator that has a very good energy resolution. An example of that would be a pure germanium detector. Germanium detectors are known for having a very high degree of energy resolution, so that you can pick out exactly what isotopes within a sample are responsible for the radiations that we are measuring. Or if you want to have a very good timing resolution, say you have an experiment where you want to measure things that both happen in two detectors at the exact same time. We call that a coincidence measurement. Then you need a detector that can very accurately measure the timing of those two occurrences and then see if they have the same or different timings. So in that case, you might decide to go with a barium fluoride crystal for your detector. Barium fluoride is a very rare, very expensive crystal material which we use in experiments which require a very high degree of timing resolution. The process of scintillation that happens in this crystal, which takes some of the energy from the energized particle and turns it into visible light, that process happens very fast in here, to the point that the peaks have time widths less than nanoseconds. Sub-nanosecond time scales here. This is to the point that the limiting factor is not our crystal, it's our electronics. It is hard to invent electronics that can keep that measurement so quick to preserve the timing resolution that we get from the crystal, to make sure that we don't lose that resolution as it goes through the PMT. And yes, this is one of the crystals that I cleaned in my original TikTok. So if you want to see me getting this crystal clean, which is already a little bit dirty, and cleaning a bunch of other these crystals, then yeah, go check that out. So then that begs the question, if we don't want to lose any of that timing information that we get from